Diode has many applications and it can be used in various types of circuits for our advantage, but it's one of the popular use is in rectifiers, and we have two types of rectifiers. One is half wave rectifier and another one is full wave rectifier. In this video, we will talk about half wave rectifier that converts AC voltage into DC voltage, and we will see how it does that. So we have a circuit with diode, and it is connected to an input voltage Vi, and this Vi is actually an AC input. Remember this. Okay, and then we have this resistor which is grounded, and we want to calculate the output voltage at this point. So this is the basic circuit of half-wave rectifier, and on the right-hand side we see an input signal which is AC input, and it has some peak-to-peak voltage Vm, and this circuit is represented by this equation Vm sine omega t in a time period of 0 to t. So let's go to the next slide, that how it works and how we can take advantage of diode in half-wave rectifiers. So in this second slide, we can see the same circuit, which is drawn at the top, and we have this sine wave, which we discussed previously. What happens in the AC voltage is that it alternates between positive and negative half cycles. So from 0 to t/2, we have this positive cycle, and from t/2, which is half time period, till the full time period, this negative half cycle. Half-wave rectifier converts AC voltage into DC voltage because we have many applications. For example, we want to charge our smartphones, we want to charge our laptops. So these devices actually accepts the input of DC current. So we need to convert these voltages to DC voltages. And before explaining how it works, we must recall this concept that the diode actually acts as a one-way valve. Okay, so if it is in forward direction, or you can say forward bias condition, then the current will flow in this way. If this is in forward bias condition, if it is in reverse bias condition, this will act as an open circuit, and if it acts as an open circuit, there will be no flow of current. You can see it over here. Just to give you a recall, forward bias condition is when a diode is connected in a way that its positive terminal is connected with the positive terminal of input source. So whenever positive terminal and positive terminal of diode, they are connected with each other, then the diode is in forward bias condition. And if it is connected with the negative terminal of the input, then it will be called reverse bias condition. In this case, we have a AC input voltage. So we talk about AC input voltage, the diode is drawn like this, plus minus, or you can see it over here. We have this input as AC. Okay, remember this. So previously I draw a battery source which was DC battery source. Now this is AC source. So when an input voltage, which is AC voltage, applied to this diode, what happens is that in this positive half cycle, which is from 0 to t/2, we will have this diode in forward bias condition. So when AC voltage is positive half cycle, the diode is in forward bias condition. Okay. If the diode is in forward bias condition, then this will be a short circuit, and we will have a flow of current in this circuit, right? In this example, we will assume that the voltage drop across diode, sorry, not voltage, the voltage drop across this component is 0, because we will assume that in forward bias condition, this will become short circuit. When there is a short circuit in the electronic circuit or mesh, then the voltage drop is assumed as 0 at that situation. So we will assume that this is short circuit in forward bias condition and voltage drop will be 0. So what happens at the output is that we will obtain, for example, this is the input. This is the input in the first half cycle. So the output will be same as this one, from 0 to t/2. Okay. And when the input voltage enters the negative phase, which is from T by 2 to T, then diode will become reverse bias. Why will it become reverse bias? Because in that situation, this terminal will be negative and this terminal will become positive of the AC voltage source. So when negative terminal will be connected with the positive terminal, this will become reverse bias. And due to reverse bias, we will assume that this is open circuit. This diode will act as an open circuit. So once this diode acts as an open circuit, there will be no flow of current and hence there will be no output voltage. So from T by 2 till T, we will have no output voltage over here. You can see it over here. Okay. So let's go to the next slide and discuss it in more detail and see what happens theoretically, and then we will do it mathematically. This is the theory which we already discussed in previous slide, that in the positive half of the input signal, we will have diode in the forward bias condition. But when the input voltage enters the negative half, right, between T and T by 2, the diode will be in reverse bias condition, not because of this, its terminal will be same as positive, negative, but the polarity of the input will change. So if for positive it was plus minus, for negative cycle it will become negative and positive. So the polarities will change, and due to that reason, the diode will act as an open circuit. So this is the theory behind that. And let's make this diagram once more. So for the positive half cycle from 0 to T by 2, the input will appear at the output. We will have some output, right? Assuming that diode is short circuit. But as soon as negative terminal or the negative part of the signal comes or appear at this input, we will have no output voltage because diode will act as an open circuit. So we will have no output between T by 2 and T. So now when this signal starts to like extend from this point, once again we will have output voltage, right? Because this again enters the positive region. But once it goes to like later on enters the negative phase once more, at that point we will once again have no output voltage. So actually what happens at the output voltage will be like we will have like this kind of ripples, or you can say fluctuations. Okay, we will have outputs only during the positive half cycle of the input voltage. So how do we calculate DC voltage from this? Let's do it mathematically. Now you can see in this figure, for the first time period, we will have an output in the positive half cycle, right? And then we will have no output between T by 2 and T. We already discussed this previously. So first of all, what we are going to do is that we are going to calculate this area under this function. Okay, so how we can do that? We know from calculus, we need to integrate this function from 0 to T by 2. So we know this function is Vi is equal to Vm sine omega t. We will assume Vm is 1 for this numerical problem. So we will be only left with sine omega t. So now we know that the integral of sine omega t is actually minus cos omega t divided by omega, and these limits will appear like this. T by 2 is the upper limit, 0 is the lower limit. So we will simplify this as 1 by omega. Now substituting the limits, so this will become cos omega T by 2 minus cos omega times 0. This is the lower limit and this is the upper limit. Now we know that for this time period, we have this formula 2 pi by omega. We know this, right? So we will substitute this t value over here. So this will become minus 1 by omega cos omega times, now t is 2 pi by omega, and then we have this 1 by 2 as well. So let me write it over here. This 2 will cancel out this 2, this omega will cancel out this omega. And this will become cos of 0 because 0 times omega will be 0. So this becomes minus 1 by omega. Now cos pi is what? You know this, right? Cos pi is minus 1. And then we have this minus sign, and cos 0 is once again 1. So the result becomes, let me write it over here. This becomes minus 1 by omega times minus 2. So this becomes 2 by omega. Okay. So the area under this signal is 2 by omega. Now, in order to convert this to DC voltage, what we have to do is we have to divide this by T. Okay, so we will obtain our DC voltage. What is that? That value is 0.318. So let me solve it over here. So this becomes VDC equal to, let me change the color of pen if I can. Let me change it to green color. No, let's change it to black color. So VDC becomes A half. A half is actually 2 by omega divided by T. T is 2 pi by omega. So we can cancel out this omega with this omega because it's in division. This 2 with this 2. So VDC becomes 1 by pi, which is equal to 0.318. Okay. So this is the same value over here. So we got the DC voltage of 0.318 for half-wave rectifier. Now the issue with half-wave rectifier is that half of the signal is lost over here. So that means we are losing half of the power. So in order to solve this issue, what we are going to do is that we are going to make a full wave rectifier. So in full wave rectifier, what happens is that for the first cycle, we will get same input at the output. But for the second half cycle, which is between T by 2 and T, this signal will be flipped and we will get it like this. So what will happen is that we will not lose any part of the input signal. So we will be solving full wave rectifier in the next video.